So before I start as well, like in going to the material, I want to give you some disclaimers, right? This is a very selective and personal perspective, right? Many reasonable people may disagree with the way I take this literature, right? And the way I take it, right? So do not take my word as the absolute truth here as well. I have a lot of horses in this race, right? So take that into account when listening to what I have to say. The other thing that I want to stress is that I have been very lucky to work with many great people in these topics, like including Jun Zhao, who is now at the University of Alabama, studying as assistant professor there, Jonathan Roth, who is at Brown, and Brent Calloway, who is at the University of Georgia. And I have learned so much from them that without this collaboration, this back and forth, I wouldn't be able to be where I am today in this topic. Right, so first, why differences and differences, right? So why we have put so much attention in discussing difference and difference methods in the last 5 years or so, and the way I see it is essentially driven by applied researchers. I saw this very nice paper, the AEA-PNP, that came out last year by Curry, Cleven, and Zuers, right? What they did is they did a text analysis, so they did kind of like a search on all NBR working papers and all top 5 papers. So among all NBR papers and all top 5 journals, right, they restrict attention to empirical papers, right? And they start searching for how often like different phrases or different combination of words appears. And like, so in this panel here, it's figure 4 of their paper. We have the frequency of differences and differences in panel A, the frequency of regression discontinuity in panel B, the frequency of event study in panel C, and the frequency of bunching in part D. So if you look at these 4 plots, right, no matter how you see them, we can all agree that is the frequency of these words appearing is increasing over time. Right? So back in the 80s, it's very rare these terms appearing, and then like as time went by, this is like kind of increasing. And that reflects the idea that like the profession become much more empirical, right? So you can see these terms being more used. But I want to call your attention here, it is not about the trends per se, but about the scale, right? So in panel A here, I have like around 22% in 2017 of all empirical NBR papers mention the word difference and differences. And to know if this is this is a big number for me no matter what, but to put that in perspective, right, we can do the same for regression discontinuity, right? And this is around 10% in 2017. So difference and differences seems to be, at least according to this metric, twice as popular as regression discontinuity. And that is kind of striking to me, at least, because as an econometrician, in the last like 15 years, we have seen a lot of advance in regression discontinuity. But until 5 years ago, there was almost no advance in difference and differences, in the econometrics literature, right? So this is kind of like, well, the way I see many of these papers appearing recently, talking about difference and difference methods, it is trying to catch up, right? So well, we have a big universe of papers, applied papers dealing with difference and differences, and the econometrics literature is trying to catch up with these new applications. But the question, again, is like, fine, what is the appeal of difference and difference methods, right? So 25%, 22% is referring to some difference and difference methods, but what's the appeal? Why do they are doing so? And why you're choosing to estimate things using DID instead of other alternative identification strategies? So again, like for very personal view, I think what DID methods try to do is to combine 2 different set of comparisons, right? So before and after, and treated and untreated groups, right? And getting these 2 type of comparisons to avoid the pitfalls, right? So what you can do here, like suppose I have variation, I have variation in timing. So I have time 0, time 1, or time 1 and time 2. And I have different groups, one group that is treated and one group that is not treated, right? In this kind of combination, I can do different comparisons. I can do before versus after, right? I can get like people who are treated before they're treated, after they are treated, right? What is the catch here? The catch is that when I'm comparing outcomes across periods, right, perhaps they're increasing, they're changing only due to like trends, right? So that's this, I mean, GDP always grow, right? So comparing before and after, gonna kind of like miss the point. So time trends gonna confound this effect. That's kind of a bummer. It's kind of a complication that may arise in practice. Another type of comparison we can make, it is like, well, let's ignore the time, like the before and after comparison. Let's do for treated versus untreated in period 2, right, in the post-treatment periods, right? But then we have a catch here as well. The catch is that, well, are these two set of units comparable, right? So are people who are treated somehow similar to people who are untreated? And this has this whole issue of selection bias, right? So is participation to treatment driven by other factors? So what difference and difference is going to try to do, it is to combine these two types of comparisons to avoid the pitfalls. Make sense? So in the canonical case, right, which I'm going to spend at least 5 to 10 minutes, I'm going to consider a setup where I have 2 time periods only. Time period 1, it is before treatment takes place, and time period 2, it is after treatment takes place. So t equals to 1 is pre, t equals to 2 is post. And I have 2 groups only, right? Group that is first treated in period 2, I'm going to denote it by g equals to 2. So g here is the time you're first treated, right? And I'm going to have a group that is at time period 2, it still remains untreated. I'm going to call it g infinity, just for the sake of the simplicity of the notation later on, right? So I have a treated group in period 2, g equals to 2, and I have an untreated group in period 2, right, which is g infinity. In this classical 2 periods 2 group case, the econometrics literature has converged that like the main parameter of interest in this setup, it is the so-called average treatment effect among treated units, right? So what is this? I'm going to look, let me just write this down. I'm going to look for the, yes, I'm going to look this first component, right? And I'm going to look for the second component as well. So what is this? This is doing it. It's looking at first at time period 2, right? I'm going to look for the outcome in period 2. And in period 2, I want to look for units who are actually exposed to treatment, right? So this 2 condition is set, like, well, among units who have been exposed to treatment by time period 2, right? What is the average like effect of being first treated in period 2 versus never being treated? Right? So this is the effect of experienced treatment like in time period 2 versus never experienced treatment whatsoever. And just to fix notation, right, I'm going to denote in the rest of the talk by y subscript t, like in parentheses is going to g, it is the potential outcome at period t if units were exposed to treatment for the first time in period g. Right, so depending on the time you're first exposed to treatment, I'm going to have different g's here. And this g, it is unnested with time period t. I have a question? Oh, good. So this is essentially, I want to recover the ATT. Among units who are exposed to treatment in period 2, right, I do observe Y2 at time period 2. So I do observe treated outcomes in period 2 for units who are actually exposed to treatment. So this first component of the ATT, it is actually recoverable from the data, right? So if I have data, so suppose I have infinite data, I observe the whole population, I can actually estimate this first component. The name of the game that we're going to play in DID, it is how to get the second component, right? Because no matter how much data I have, among units who are actually exposed to treatment, I never observe their untreated outcome, right? So suppose in In the US, there is a lot of debate about COVID vaccines, right? Let's say treatment is receiving like one of the vaccines. And also I want to see the effect, my mortality rate, my mortality index, right? Given that I have received the vaccine, I want to see what is the average effect of the vaccine on mortality rates, right? Among units who actually took the vaccine. Right? So among those who took the shot, I can compute this, right? And then this guy here, among units who actually took the shot, I never want to know the outcome in the absence of the shot because I only see one universe. I don't see a parallel universe where I can observe both YT2 and YT infinity. Right, so this is going to be the hard component to recover. We all know that it's classical case for the DID and for the any causal inference procedure. So how are we going to recover that? There is only one way to recover. It is by imposing assumptions, right? And the assumptions we're going to impose in DID is going to be two main assumptions. The first one is a no anticipation assumption. We're telling that like that is before treatment takes place, there is no treatment effect. That's what's written here. So in period 1, nobody's treated, right? So I always observe the untreated potential outcome. That's what's written here, right? This assumption is reasonable in setups in where treatment is not announced in advance. So if I tell you today, like Stanislaw going to be treated in 10 days from today, right? He knows that today, he may change his behavior today and take into account that treatment in 10 days from today. So in those situations, this assumption is going to be trickier to hold, right? But for the sake of the argument, let's impose that we are not in that word. So treatment is not announced in advance, right? Treatment is unanticipated. Usually this assumption is embedded in the potential outcome notation, right? So here I'm trying to disembed it from the notation to make things slightly more transparent. Then we have the classical assumption, right? The non-anticipation per se, it is not enough. So we're going to go beyond. We're going to say, well, I have this parallel trend assumption, right? Which is just telling that like in the absence of treatment, right? The average evolution of the outcome across treated units, it is on average the same as the evolution of the outcome among untreated units. Why this assumption is useful for us, right, is essentially this is what we're trying to learn, right? So the expected value of y at time period 2 in the absence of treatment, right, among treated units. So this is not recoverable from the data, right? So this is going to be the hard one. Let me make this spotlight. But I can manipulate, right? So I can get this guy on the other side and manipulate it. So once I have that, everything here on the right-hand side, it is estimable from the data because among untreated units, I always observed untreated potential outcomes, right? And by the non-anticipation assumption, this guy here, I can put this at 2 inside. There is no big deal by this. So that's going to allow us to like impute expected values of untreated outcome period 2 among treated units. And that's going to solve the identification challenge, right? So once we solve the identification challenge, right, it comes from estimation. Then it's the birth of the DID estimator, right? We could just compare, take the first difference of the outcome, take the average in treated group in period 2, the average of the treated group in period 1, right? And subtract one from another. Do the same thing now for untreated group, subtract one from another, and I have a difference in difference procedure. Now, in practice, I usually don't see people doing things like this. I call this like brute force difference in difference procedure, right? Because I'm working for identification and mapping the identification arguments to the estimation, right? So I've seen DID by hand or DID by brute force. In practice, people do not do this. So in practice, what people tend to do in this canonical setup is like, well, you know what? I was trained to run regressions since I start college, right? So Stats 101, we first learned comparison of means in Stats 101 in undergrad. But as soon as we are done with comparison of means, we go straight to regressions. And once we enter the regression word, we never get out of that word. Right? So once we learn regression, we stick to regression for the rest of our lives as economists, most of us at least. Right? So this regression has a lot of familiarity to us and a lot of appeal because we kind of like know a lot about regressions. So instead of doing this comparison of means or DID by brute force, what I'm going to do, I'm going to run a regression of the outcome for unit I impurity against an intercept, against a group dummy, right? So this is a dummy variable if I am treated or not, right? A post-treatment dummy, and the interaction between group and post. And it's very easy to show that the beta that I have here, beta naught 2a fixed effects from this canonical specification, gonna be numerically the same as this theta hat n here. Right, so this is a numerical equivalence. So you run this regression, estimate this beta naught 2a fixed effects by OLS. It's gonna be exactly the same as theta hat DID, which is good, right? Because then it's showing like, well, indeed, OLS is doing what it's supposed to do it. So far, so good. And then what we do, once we have this, we can do inference, right? We can, it's a regression procedure. We learn how to run regressions. We learn how to do inference. We can do cluster robust inference. We can do heterostochastic robust inference. You can do bootstrap. We can do all the mumbo jumbo we learn about regressions in this setup in a very straightforward manner. What is the catch? There's always a catch, right? So this is where the new literature is going to come through it. The catch is that this equivalence, it's very well like understood, like, but this equivalence holds in the canonical setup with 2 groups and 2 treatment periods only, right? In practice, when you open that universe of difference and difference papers, right, most of those papers going to deviate from the canonical 2 groups and 2 time period setup, right? They're going to deviate in different ways, but they usually going to deviate, right? So here I have listed several types of deviations, and this is important, right? So many of these difference and difference procedures I'm not going to have only group and outcomes, right? I'm also going to have covariates available. And once I have covariates available, I want to allow for covariate specific trends, right? So for example, people in the northeast of the US tends to be very different from people from the south of the US, right? So the outcomes may evolve differently according to the region, right? Or people in Europe is different from people in Latin America. I want to allow for like region-specific trends. So whenever I want to do something like that, right, covariate is going to play an important role. Another thing that has seen a lot of like action, and it's very common applications, it is that we do not have only 2 time periods. We may have more than 2 time periods. We have many time periods. And once we have several time periods, it is only fair to allow for people to be treated in different points in time, right? So once we allow for multiple time periods, it is natural to allow for variation in treatment timing, right? So this means that like I may be treated today, right? But like Andres is going to be treated in 10 days from now. Stanislaw going to be treated in 20 days from now. Like Jesus is going to be treated in 15 days from now. And we have every people may be treated in a different cohort, right? Which is fair game, right? No minimum wage. Like states may raise their state level minimum wage in the US in different points in time, right? So different neighborhoods may pass different policies in different points in time, and so on and so forth. This is going to be in this case. Again, once we have that, we are outside the classical 2x2 DID setup. We also have this idea of like I have non-binary treatments, right? So perhaps I want to exploit dosage variation in the treatment, right? So my treatment is like how close I am to like, I don't know, an event, right? So the further away, the less the dosage. So this is going to be non-canonical as well. But I have multivariate treatment. So like I want to see the effect of taking 1 aspirin versus 2 versus 3 versus 4, right? So then I am outside this binary word is going to lead to new complications as well. Other situations, I want to have treatment to turn it on and turn off, right? So suppose I'm exposed to treatment today, right? Tomorrow I am not anymore. How can I accommodate treatment turning on and off? Sometimes, as I mentioned earlier, I'm going to have treatment anticipation. So if treatment is announced in advance, how do non-anticipation assumption is kind of not very reasonable. So how can I allow for that flexibility? And finally, we also can think about parallel trends do not hold exactly, but hold approximately, what approximately means. Right? So all these going to be situations when you're going to deviate from the canonical 2x2 setup. And once we deviate to the canonical 2x2 setup, I have this big warning here. It is like, well, you can still run regressions. You can always run regressions. Regressions are free. It's cheap. You put in the computer, you press enter, it runs. The caution here, it is what is going to be spit out from that regression, right? So under which assumptions, like what kind of assumptions do I have to impose such that I can interpret the output of those regressions in a clear way? So that's where I think is like the literature is kind of going right now. Right, so the way I see it is that once I have this plethora of deviations from the 2x2 setup, this is where econometrics start catching up with empirical practice. Right? So this is a literature that is driven by practitioners. So empirical researchers have problems. You don't have a solution. What you do the best you can given the tools that you have, right? And that's totally fair, totally game. Then us, econometricians, start seeing those things and start asking questions. Well, it is actually the best we can do. I mean, in this setup, is this the best we can do? Right? What else can we do? I mean, is this actually getting you what you actually want? And this is how this new literature on difference and difference comes into play. Right? So the new literature on difference and difference is going to come to play is like, let's entertain all these different possibilities. Sometimes only one, sometimes several of them together. Let's put all this into this like blender and see what's going to come out of that. Make sense? So the way I think the literature on difference and difference is going at the moment, it is to allow for several of these setups in a given context. But I'm going to try to summarize some of these recent papers in a 1 or 2 sentences. Then I'm going to illustrate the big action here when I have more than 2 time periods and variations treatment timing, which is the area we have seen most papers talking about it here. Cool? Any questions so far? Yes.
Hi, Pedro. I just wanted to ask you if in the review you're going to do, when you say recent, you include the paper from Woolrich he published.
I'm not that recent, right? I mean, I have seen his. I mean, I have seen him presenting an early version of that paper last year, right? I mean, actually, I have seen him present that paper twice. I discussed with him, but I haven't seen the very new last version. And the very new last version that he has apparently has some kind of like new results. And those new results are the interesting for me, right? Like what to do if everybody is treated, how you can get the treatment effect of this last cohort, this last time periods. He says that he can recover those. I have no clue how he does it, right? So I'm very curious to read. So yeah, we messaged each other. We talked a little bit, but I haven't read it in great detail. But hopefully I will do this in this weekend, because next week I'm teaching a difference and difference course, and this question is going to come at least 10 times. So I have to be ready.
Thank you.
Yeah. More questions? I like questions, guys. Please help me here as well. Good. So I'm going to first talk about the role played by covariates, right, in difference and difference setups. And I'm going to be very brief here, right? This is, because I'm going to talk about a paper of mine, right? So this paper with Jun Zhao came out in Journal of Econometrics in 2020, right? And the idea here, we are in a very simple setup. We are in a 2 periods, 2 groups setup, right? But then we are in a world where we want to allow for covariate specific trends. Once we want to allow for covariate specific trends, we know from the previous literature that there are 2 main guided ways of doing that. One is using regressions, right? When I say here using regressions, I'm going to have an outcome regression approach. It is different than using 2-way fixed effects, right? Because regression here going to means I'm going to like subset the data among treated units, right? And run a regression for the first difference of the outcome against covariates on that treated units. You do the same thing now for the untreated units. Subset the data to only look at untreated units, run an OLS if you want in the untreated units, right? And the outcome is going to be the first difference of the outcome. Then you get a prediction of these 2 regressions, right? You take the difference in predictions, then you average the difference in predictions among units who are actually treated. This is going to give you the outcome regression approach that was first discussed by Jim Heckman, Hideichi Mura, and Pedro Todd in 1997, right, in Ristad paper. An alternative approach that does not rely on modeling the outcome regression per se, it is what was proposed by Alberto Abadi in 2005, right, is using inverse probability weighting. So this is going to model the probability of being in the treated group, right? And once I have a model for that, I can reweight treated and untreated outcomes, right, to recover the ATT. So I have asked myself the same questions 1 million times, right? So that's how I end up writing this paper with June. So I have the outcome regression model. I have the IPW. Which one do I choose, right? They both recovering the ATT. But if I have to pick one of them, how I'm going to pick? And that's a very hard question from my perspective, because this, although I'm trying to recover the same target parameter, the path that I'm following to get there, it is very different, right? So outcome regression going to rely on having a good model for the outcome evolution, right? IPW methods going to rely on having a good model for the propensity score, and sometimes I have one better than the other. So what June and we did in this paper, it is instead of choosing between the 2, let's combine the 2, right? So instead of choosing between outcome regression and IPW, let's merge them, right? But let's merge them in a guided way such that as long as one of these 2 procedures here, IPW or outcome regression, it is okay, the result here is going to be okay as well. So essentially, we are giving 2 shots, right? So essentially, I'm giving you 2 darts. You can throw a dart first. We're going to call this first dart outcome regression, right? You're going to throw a second dart, the IPW. As long as one of the 2 darts hit your target, you're good to go, right? Whereas if you do like Heckman et al. Or Abadi, you're going to have only one dart. So we're leaving money on the table. So that's the idea here of double robustness, right? And that's one appeal of doing what we propose in that paper. Everybody who has read or heard about machine learning, right? They know one of the key features of using a machine learning procedures as a first step estimators, it is to have this locally robust score, right? Or the Neyman orthogonality moments. This is what the double robustness procedure here is doing for you. So if you want to do machine learning difference and differences, for example, you're going to have to use like the formula that we propose here, right? But you can use flexible models for the outcome regression, flexible models for the IPW. So this is where I think like we are heading. Also in terms of efficiency, right? In this paper, we say, well, if you assume only parallel trends and you assume non-anticipation, what is the best you can do, right? So what is the benchmark in terms of the shortest confidence interval you can ever hope to get, right? And we say like, we establish that benchmark, we derive the same parametric efficiency bound, and we have shown that our estimator asymptotically reach that efficiency bound. But I think the main message of this paper, Sant'Anna and Zhao, right, or SZ, it is that adding covariates linearly in your two-way fixed effects. So I have this regression here. I add a vector of x prime beta here, right? Or x prime gamma, let's say, right? Or x prime theta, whatever you want to call it. What is saying, what that paper shows, it is that this beta here not gonna be an ATT anymore. The beta, so adding extra terms here, gonna mess up the interpretation of the ATT, right? And why is that? Because essentially we are imposing more restrictions than we want to. So in general, adding covariates linearly into a fixed effects will not give you the ATT. It's going to have some problems. We do more in that paper. Yes.
One question. One approach that is very common in the empirical literature is trying to use like interacting some baseline covariates with trends, stuff like that. This critique that you are mentioning is, I imagine, is pretty general. It doesn't matter whether you add the covariates in any way, just adding covariates creates this problem.
So if you interact the covariates with the time trends, right, the problem is going to be substantially reduced.
Okay.
If you multiply the covariates with the time trends and the group dummy, it's all gone. Right? Because what is going on? You can remember, like when you do interaction regression, so what we are doing here, this outcome regression approach, it is subsetting the data and taking the first difference, regressing the first difference on covariates X. Right? So this is equivalent of interacting the time dummy with the covariates and the time dummy with the covariates and the group dummy. Right, I'm going to have this long, I think like Jeff Aldrich called this the long regression. And that's going to be numerically equivalent of doing the outcome regression approach. This problem going to go away as long as your model for the outcome evolution, it is good to go. The big problem, it is adding covariates linearly here without the interactions. Make sense?
Okay.
So just a follow-up of that, Pedro. Hi, I'm Juan. So
yes,
just a follow-up of that discussion is that if you, one second, sorry. I'm sorry. I just received a call, I'm sorry. So this messed up my
right on time, huh?
Yeah, okay, I'm here.
That's a good friend. I bet it's somebody in the audience that saw you going to ask a question and just called you.
It's actually my wife. So, but I don't want to miss the opportunity to ask this question. So if you actually, you need, for the outcome base, you need to have a good model of the outcome, right? So,
yes.
So if imagine that you know what are the covariates that actually are best predictors of the outcome. If you have that, if you have those covariates and you add them interacted with the linear, with the trends and with the trends and the group dummy, that would solve the problem. That's equivalent to using the machine learning approach of choosing the right covariates that predict better the outcome and interacting them with the year fixed effects. But what you would add to that is that you also have to interact them with the year fixed effects and the treatment dummy, right?
Yes. So the issue with machine learning, you have an additional layer of complication because you're also doing model selection, right? And the model selection is what's going to destroy inference. Because if you do machine learning and you allow for making mistakes, right? So, I mean, let's say like very often I get the good covariate that matter, but sometimes I mess it up. I make mistakes. I pick some that are like not so good, or I leave some good ones. Like I fail to pick the good ones. So if you allow for mistakes, right, you're doing essentially model selection, and then the outcome regression procedure gonna be complicated. So so once you allow for mistakes in machine learning, you have to kind of like use the double robustness, because it's essentially, you're gonna do model selection for the outcome, you're gonna do model selection for the propensity score. And then the errors of these two model selections are gonna enter multiplicatively. So it's like, well, something that is small times something that is small is, I mean, is epsilon times epsilon, right? It's like much smaller than 1 epsilon. And that's the idea here. But if you ignore model selection, right? Let's say I don't have any issue with model selection. I know what covariates matter for the trend, right? You can just interact all of them. And this is going to be equivalent to what this outcome evaluation procedure is going to do, right? And this is going to be good to go. All these problems with the ATT here, with two fixed effects, it is depending on the way you add covariates. And that's important. If you add covariates in a flexible way, I mean, you can't be, I mean, if you, once you allow for covariates in a very flexible form, it is very hard to beat regression. So all the problems we're going to see in all these different procedures comes specifically from the way people add covariates, or the way people like include fixed effects. Is very like tiny details that's going to really matter. Make sense?
Yeah, thanks.
So yes. So yeah, so in the paper as well, like that I wrote with John, we have this is a question that I had for many years. It is like, suppose I have panel data, right? How much how much should somebody pay me, right? In terms of data, such that I can I can give up panel to repeated cross sections. Let's put it this way. Suppose I have two options, right? I can follow everybody in my sample, right, across time, but that's going to be much more costly, so I'm going to have a smaller sample. Or I have, like, every period in time, I can sample new people, but that's cheaper, and I'm going to have a higher sample size. So how much bigger the sample size has to be such that I get the same precision in both procedures, right? So that is a question in terms of like how more efficient it is panel data with respect to repeated cross sections, right? And we characterize those efficiency gains in this paper as well, right? I mean, I had never seen anybody talking about this, but I really like that result, right? Because this took me forever to derive, so I'm here mentioning it as a self-advertising as well. So this paper came all about the role played by covariates in the 2x2 setup, right? So 2 periods, 2 groups, everything is very simple. But the way you add covariates, you can get additional robustness, and you can also get efficiency gains by modeling the both parts of the data generating process. Cool. But that's 2x2, right? I mean, this is kind of like old game. Nobody talked about this anymore. There is a new king in town, which is variation treatment timing, right? And staggered adoption. So what happens if we allow, so I'm going to go now, turn the page and look for a different type of problem. So instead of having the 2x2 case, I'm going to now have multiple time periods, and I'm going to allow for people to be treated in different points in time, right? So when I have this variation treatment timing, and I also have multiple time periods, it is extremely tempting, right, to extrapolate from the two-way fixed effects regression, because this is very easy to see as a like generalization of the canonical regression we have talked about in a minute ago, right? But because instead of having a group dummy, I'm going to have unit-specific fixed effects, much richer, right? Because it's unit-specific. I'm allowing for time invariant unobservables to affect my outcome. Instead of having a post-treatment dummy, I'm going to allow for time-specific fixed effects. Again, more general. And instead of having the interaction, I'm just going to replace the interaction, right, post with group, with this dummy variable dit, which takes value 1 if a unit I is treated by period t, and 0 otherwise. Right, so this regression, it is very natural for us to run. And in fact, this has been one of the most popular specifications in the whole empirical literature running DID type methods. But the question is, well, we know if everybody, first, what this regression is assuming it, right? Staring at this regression, right, we essentially, implicitly, we assume that all units have the same beta, right? So there is somehow an homogeneous treatment effect assumption behind the scenes here. If treatment effect is the same for all individuals and for all time periods t, this is good. You can't beat this because I have a correctly specified regression approach. The question is, what happens when I am not in that world, right? So what happens, right, if I am in a heterogeneous world where treatment effects can vary across individuals and can vary across time as well, right? So this is going to be the question we're going to try to answer at the moment. In a world with heterogeneous effects, right, and heterogeneity here can be with respect to dynamics, or can be also with respect to different units have different effects. In that world, what does beta recover, right? So what does beta recover in this world of heterogeneous treatment effects? And this has been one of the most active areas of research in the last 4 years or so, right? Is trying to answer that question. Right? So there are several papers tackling this problem. Right? So Borussiak and Jaravel, and they have a new version, Borussiak, Jaravel, and Spies, right? 2021. But I'm citing here the early one just to make sure the time frame is correct. But they were way early. Deschamps-Martin and Dalton Fourier had this 2020 AER paper. So Andrew Goodman-Bacon has the Journal of Econometrics paper, and Susan Athey and Hido Ibens also have this Journal of Econometrics paper. All these papers are trying to answer this question. What is beta? I mean, beta is beta. We all know that, right? But if I have to give a causal name for beta here, what it is? It is the average treatment effect on the treated, right? It is the overall average treatment effect, right? It is the weighted average of treatment effects, but what are the weights? So all these papers here are trying to characterize the meaning of beta in a world with heterogeneous treatment effects. Make sense? They're going to have different assumptions. So for example, Athey and Ibens have the most restricted set of assumptions because they assume the treatment selection, it is completely random. They don't have a parallel trends. They have essentially a randomized control trial, which is much stronger, right? But they still have the composition results. So Athey and Ibens is going to have a strong set of assumptions. Like Borussiak and Jaravel, the original version was kind of very parametric. They imposed some homogeneity assumptions behind the scenes, right? Deschamps-Martin and Dalton Fourier, they allow treatment to turn on and turn off, but they only restrict attention to instantaneous treatment effects, right? And then Goodman-Bacon does not allow treatment to turn on and turn off, but he allows to dynamics. So all these papers are going to provide different types of decomposition results, trying to answer what is beta in this heterogeneous world. The big message that I get of no matter how you read, and by the way, these decompositions are all different. They have different building blocks. The message is the same, but the building blocks differ. Right? So these papers are highly complementary of each other. The main message that these papers give, at least to me, it is that in a world of heterogeneous effects, this is a very hard to interpret regression, right? Because beta going to recover a weighted average of cohort-specific treatment effects, but some of these weights are negative. And why this is a problem? Because if I have some weights that are negative, in a world where all my ATTs are positive, I'm average, then some of them going to have positive sign in my average. Some of them going to have a negative sign in my average. So if the negative ones dominate the positive ones, I'm going to have a negative beta, even when treatment effect is good for everybody. So this can be very misleading for policy recommendations. Make sense? And this is what everybody talks about, like the negative weights in the two-way fixed effects model, right? This is what, like, when people talk about the Bacon decomposition, people are going to talk about this specification, right? Is actually opening up beta in terms of building blocks. Any question about this? If you submit the paper and you run this regression, right, you're gonna for sure be asked these days to try the Sant'Anna and Alto-Follier like diagnostic test, or look at the Bacon decomposition as well, right? This has been extremely popular. So one remark, right? So if you're looking for negative weights, the Bacon decomposition, right, never gonna give you negative weights, right? If the output of the Bacon decomposition in theta or in R, never gonna give you negative weights, because the Bacon decomposition is writing beta here. Some of these negative weights are implicit there. So to answer, is negative weight a big problem for my own application, right? This is the Sant'Anna and Alto-Follier, right? They have this negative weighting explicit as the output of their software. So just to give like an overall idea, they have different building blocks. Cool. So what about the second variation, right? So we have other variations as well. We do this. So this is a static regression, right? I'm only learning one single parameter. But in many situations, if I have multiple time periods, right? I wanna like take a deep dive in that setup and learn about treatment effect dynamics. Because the beauty of observing several time periods, right? It is that I can talk about how treatment effects evolve on average over time since treatment was adopted. And in that word, we have a variation of the classical two-way fixed effects regression, right? And this is like what is called a two-way fixed effect event study specification. So instead of having the single beta coefficient over there, I'm going to keep the unit-specific fixed effects. I'm going to keep the time-specific fixed effects, but now I'm going to replace that beta with several leads and lags. Right? So leads here, what I have here in orange, it is supposed to capture violations of treatment of parallel trends or violation of treatment effect anticipation. So this DIT K, when K is negative, it is asking unit I in period T if this unit going to be treated in K periods from now. Right? So let's take K here equals to -2. So I'm asking Stanislaw today if you're going to be treated in 2 days from today, in 2 periods from today. Right? When K is -3, I'm asking Stanislaw if you're going to be treated in 3 days from now. Those are like leading indicators of treatment. Right? So this, because this DITs here is about the future, right? Today, if I do not have treatment effect anticipation, I'm a pre-treatment period. So presumably, all my gamma K's leads should be equal to 0 if all my assumptions are okay, are satisfied. Right? And here, so this is like presumably, I would like to see all these gamma K leads equals to 0. What about gamma K lags? This is supposed to capture how treatment effects evolved with elapsed treatment timing. Right? So K equals to 0 going to be the instantaneous treatment effect. Like a lag, yeah. So K equals to 1 going to be the effect 1 period after I was treated. K is to the treatment effect 2 periods after I am treated, and so on and so forth. And I have this like binning parameters here, because sometimes you say, well, I don't want to include all leads and lags. I only care about some leads and some lags, so I can bin these other extremes. You don't have to, but some people do it, so I include here for generality. Right, so the natural question here is like, well, we have seen that in this world, beta is complicated. And one of the main reasons for beta have these negative weights was about treatment effect dynamics. Right? So the Bacon result here, the Goodman-Bacon result, showed like one of the main complications is dynamics. So here, I'm explicitly modeling some dynamics. So the question was like, well, if I model dynamics, do I solve the problem or not? And that's what is at the heart of Sun and Abraham 2020 Uniform Econometrics paper. Right? What they are doing it is like, let me better understand these gamma leads and gamma lags and see if they actually recover some useful causal parameters in a world where treatment effects are heterogeneous. For me, the biggest message of Sun and Abraham, it is that gamma K leads, like the pre-treatment coefficients, right? They are contaminated with post-treatment coefficients. So even when I have no treatment effect whatsoever before treatment takes place, I have parallel trends, and I also have no anticipation, these gamma K leads can be non-zero, right? Because they are contaminated with the post-treatment period dummies, right? And why this is problematic? Because the common practice of looking for these gamma leads and interpret them as pre-trends, it is misleading. Right? So if I have dynamics, this can be non-zero even when my assumptions are satisfied. Same thing is true for the lags, right? So we should be very careful on interpreting lags here because they are not appropriate measures of treatment effect dynamics when treatment effects are actually heterogeneous. So they also have this kind of a negative weighting taste here on the lags. So Sun and Abraham is also kind of like quote unquote negative message that 2A fixed effects, it is not so cool. Make sense? And again, this is like if you interact these event dummies with cohorts, many of these problems are going to go away. This is all about this particular type of specification when you don't have many interactions. Right? So the way I see all these problems with 2A fixed effects, right, either the static version or the dynamic version, it is that OLS is variational hungry, right? OLS doesn't care about causal inference whatsoever. OLS cares about minimizing mean square error, right? And to minimize mean square error, what I'm going to do? I'm going to try to leverage every single comparison that I can in my data set, right? So I'm going to compare early treated versus later treated. I'm going to compare later treated versus early treated. I'm going to do every single comparisons such that I see variation in treatment status, right? I'm going to compare them because I'm aiming to minimize mean square error. But causal inference takes the opposite path. Causal inference is all about being very cautious which comparisons you make. So I always say like causal inference is variational cautious. I'm not going to compare every group with other groups. I want to handpick. This is a good comparison group. This is a bad comparison group, right? We want to leverage the good variation and ignore the bad variation. And OLS is not the right tool to do this all the time. So once we realize that the problem is that the goals here are not aligned, we can move forward, right? So this is like how we can solve these problems of 2A fixed effect specifications. So it's all about ensuring the comparisons you want to make, right? So I want to compare group A with group B, group A with group C, group A with group D. I can pick that. I do whatever I want. It's my paper. It is my estimation method. So once we have a procedure that allows us to make the comparison that you want to, we are good to go. All these problems of negative weighting, like contamination effects, gonna go away, right? And this is what Brent and I proposed in our 2020 Uniform Econometrics paper. right? So the main message of Callaway and Sant'Anna, it is, let's be a bit more cautious about jumping to regressions too fast, right? Let's split our analysis into three main building blocks. First, let's talk about what you care, what you're trying to learn. This, what we call the ATTGTs. So the average treatment effect for a given cohort in a given point in time. Once we fixed the identification assumptions, once we fix like the building block, we can talk about how to average them, right? And how to estimate and make inference. So identification gonna give us which comparisons we wanna make, right? Aggregation is gonna tell like how to aggregate these comparisons into a smaller number of parameters, right? And then estimation and inference is how to bring this to the data. Right? So the way I see, if I have these three steps separately, all these problems are gonna go away, right? And we are not the only game in town who's doing this. So San Abraham also have some results on this. The Charles Martin and Dr. Follier also have some results on this. Right? San Abraham, none of these papers actually allow for covariates, right? And the Charles Martin and Dr. Follier is focusing only on instantaneous treatment effects, right? So they are completely silent about treatment effect dynamics. They have follow-up papers that do handle treatment effect dynamics, but they came out like 1 or 2 years after San Abraham and Callaway and Sant'Anna, right? So it's there. Good. So that's the way I see this literature. So we have some, I like to split these papers into two like categories: diagnostics and solutions. Diagnostics is like taking toys away, right? Or pointing fingers. And many papers are doing that, right? So this whole building block here is doing that, taking toys away, criticizing this specification, right? And the other branch of the literature is about proposing solutions, right? So it's like giving you new toys. And I think like Callaway and Sant'Anna is also in the later category. Many papers are in both category, right? So San Abraham and Charles Martin and Dr. Follier are in both. But yeah, that's the way I see it. I'm out of time already, I'm pretty sure, right? But I just want to give you like a illustration of these problems in practice in a very stylized like simulation exercise. When I have this to me, you most likely have seen this if you follow me on Twitter, or if you follow any of us on the people on Twitter, you have seen this type of plots before. This is inspired by Andrew Baker simulation results in their paper. Right, so this I have a very stylized example. When I have 4 different cohorts, right, and everybody is eventually treated. So the red cohort, it is first treated in 1986. The blue cohort, it is first treated in 1992. The green cohort in 1998, and the purple cohort in 2004. Everybody has different dynamics. So I have a lot of heterogeneity going on here. Right? So before treatment takes place, everything is parallel. Right? Everything is parallel before treatment takes place. But once treatment hits, you diverge. Right? Have a trending treatment effect. So the way, this DGP, the way I assign people to these groups, it is a completely random manner. So I have an RCT in time, right? So just to make things very simple, I do have an RCT in time. So that is parallel trend satisfied, non-anticipation satisfied by construction. Here I have a description of the DGP, but for the purpose of this illustration, I don't have to go into the detail, right? It's just to make sure like I'm not cheating, right? I'm respecting all the assumptions of every difference and difference procedure, right? I'm actually imposing more than I need to. So in that figure, I really like this figure because I think this is like, when I see flat pre-trends like this, I'm like, well, this is a good setup for DID. It's very convincing. Just plotting the series like this gives me a lot of like confidence and excitement to use DID as my research design. So what I'm gonna do, I'm gonna run this 2A fixed effects event study specification, right? I'm going to set the leads and the lags to 5, and I'm going to bin everything that is more than -5, bigger than 5 together, right? Because I want to look at the event time window from -5 to +5. I want to see if these effects recover. I'm going to do this 1,000 times, compute bias and simulate some errors and plot them. Once I do it, this is what I get. Right, so the red one, it is a true, quote unquote, pseudo true, right, weighted average of these event studies. And the red one here is what I get on average. There is no standard error visible because they are so tiny, right? The procedure is very precise. And what is striking for me, it is to see these violations are like visible violations of pre-trends. So if I give you this red curve, right, as your empirical research, and you submit this paper to your, first, once you see this striking pre-trends, you most likely kill the project, right? Because, well, you know what? There's a lot of variation taking place before treatment starts. So I have pre-trends, right? And then I don't know what to do it, right? So essentially, you're going to interpret this as like the DID being not the right tool for you, when in fact it is. I mean, the red one, it's a flat line at 0. And this is essentially why this is happening. This is happening because of what Sun and Abraham made explicit in their paper. Treatment leads are getting contaminated with treatment lags, right? So what something's supposed to be here is being captured here. So I see these violations. And that's not a failure of the design. It is a failure of the estimation method you use, right? So this, you look at this and say, oh my God, I'm very off. But then you look at me and say, you know what, Pedro, you are cheating because you're binning these things to 5 and -5. Let's not bin. Let's add all possible leads and all possible lags. Much more flexible. But then I'm going to zoom in. I'm only going to report the coefficients from -5 to 5. This is what I'm doing here. Like, no, this is fair game. I can do that, right? I can add all leads. I can add all lags, and I'll report the window that you care about. You do this, now it's much less precise, but the problems are still here, right? So I have like violations of pre-trends, right? And I have everything here. I mean, the true one is, and I have very negative treatment effects. So again, not very comfortable, not the right tool to tackle this problem. So the question is, so these are like the problems alluded and made explicit in Sun and Abraham. The question is, there hope? There is always hope, right? This is what my paper with Brent comes and say, well, if you choose the comparisons group that you actually want to use it, right? So here should be the not never treated, like the last cohort as the comparison group, you get precise effects. This should be Calloway and Sant'Anna and Sun and Abraham. This is what both of us are doing it. If you want to use the not yet treated unit as a comparison group, right, you get very precise estimates as well. So this is all to stress that the problems, like of the difference in difference, the variation treatment timing, it is not about the difference in difference per se, but it's a problem of the specification you're using it, right? And I have like 1 gazillion other slides on zooming in how we solve the problem, right? I'm happy to share these slides as well, but for the interest of time, I'm not gonna go zoom in. I mean, and if anybody has any question about any of this that you're gonna see here, the main message, it is to separate identification, aggregation, and estimation and inference, which I walk you through in these slides one by one, more I mean by each of them, right? So I'm gonna share the slide with Stanislaw, and feel free to distribute to the class as well and to everybody. I mean, and I have a more general version of Calloway and Sant'Anna slides deck on my webpage, right? I have written a lot of like blog posts on this. Feel free to use them, modify them, reach out to me. And that's all I have to say for today, right?
Thank you, Pedro. Thank you for your time. It was a very nice presentation. And you know, we hope that we can plan this course that we are thinking of soon so we can go over the details about this. We are about the time limit. Thank you so much, Pedro. Again, thank you everyone for joining today. I don't know whether someone else have a final question before finishing.
I'm happy to stick around a bit more if anybody has questions or want to chat about differences, like what it means one procedure versus another. I mean, more than happy to stay here a bit longer if anybody wants to ask questions on those things.
I'll take you on that because I guess you mentioned the like 10 things where the traditional two-way fixed effects might fail, but you didn't get to talk, or there is no literature. I guess I wanted to check on treatment turning on and off.
So on and off. So on and off with instantaneous treatments, right? So let's put it this way: if treatment turn on and turn off, and I know for sure the treatment lasts only for one period, I had this no carryover assumption. That's in the Scheiss-Martin and Alto-Fourier, right? They cover that fully, but only for instantaneous treatment effects.
Yes.
Now, suppose that I want to also, I want to learn about dynamics, right? They have a new version, the Scheiss-Martin and Alto-Fourier, so Clément and Xavier. They also talk about how to recover dynamics, right? In this turning on and turning off. And this is kind of an IV type of procedure. The new paper is called Intertemporal Treatment Effects, Difference and Difference. I mean, go to Clément's webpage and whatever starts with intertemporal, that's the paper that covers it. They have Steyr code as well, right? So they covered this. But the idea is like this. So how do they tackle it? Turning on and turning off, right? So how can I actually answer those questions? If I do not want to impose a carryover assumption, right? And when I say carryover, it's like, well, I don't know for how long the treatment lasts. I'm not willing to take a stand on how long it lasts. So I'm going to have to create kind of a quote unquote fake treatment times. And I'm going to map everything back to the staggered case. I'm going to create group dummies for the first time the treatment turns on ever. Right? So once I have that measure, the first time I try to turn on average, I'm back to staggered. So what they do an event study with the first time I'm on the outcomes. They do a staggered for the first time I am on, but on the treatments that is on and off in the treatment status, DI, and I take the ratio of the two. Right? So this is going to give me a per time exposure, per time exposed to treatment measure, like average, and that's going to allows you to do it. I have a hard time doing that because you end up aggregating too much. Because turning from 0 to 1, then 0, let's put this 0, 1, 0, 1, 0, 1 forever. It is the same as 0, 1, 1, 1, 1, 1, and 0 in the last period. So I'm aggregating these two cohorts who are arguably very different in the same parameter. Right? So that's the solution they propose. On the other hand, I don't know any other better solution. Right? So what they're proposing, I think is at the moment is the best we can do. I have a hard time giving interesting interpretation out of that, but I don't have any other thing to do it. So it's that's what we have to settle to that. So on and off, so Clément and Xavier are the experts on this. So they have these things, yeah. They also have a new paper, so taking the jump, on units being treated to different treatments over time. So it's I am treated today, I received today treatment A, tomorrow B, then later on C, right? So how do I handle those situations? So they have a paper on this issue as well, and it turns out two-way fixed effect does a much worse job there than before. So the negative weights are much more severe. Right, so that's something as well. Another thing that I didn't mention, that I didn't have time, it is what to do when you have like parallel trends not holding exactly, but hold approximately. And that's the work of Jonathan Roth and Ashish Rambadashan. They have this working paper, like honest difference and difference procedures. I really, really, really like that paper. That is my favorite paper among all difference and difference papers in the last 5 years or so, right? And it's kind of like doing sensitivity analysis in that word.
Paul has a question, and also Andres.
Yes, hi Pedro. My
Hi.
case is, so it is quite different, but sometimes I see it related, is the role of synthetic controls. So because it kind of tried this idea of getting better the identification and then the right comparison against the groups. I don't know if there is something that combines both ideas.
So the way that's a great question, because I'm going to give you two answers, right? The first answer is going to be a bit spicy answer. Then I'm going to give you the scientific answer. The first answer is like, I have no clue what is the identification assumption behind synthetic controls. If you give me any paper that tells me the identifying assumption, it is A, B, and C, I'm happy. None of those papers mention this. None of the classical Abadi papers tell me what is the identifying assumption, right? Which is very hard. So if I have all the data in the world, right, how can I get my parameter of interest? They don't mention any of that. So that's the first thing. So it's very hard for me to compare from the identification perspective, difference and difference of synthetic control, because synthetic control is not explicit about identifying assumptions. Difference and difference is very clear. It's a parallel trend. You may not like parallel trend. I personally do not love it, but at least I know what I mean. I have the rules of the game set. That's the spicy, kind of like nagging answer. I'm going to give another scientific answer, right? So the way I view synthetic controls, it is doing selection on lagged outcomes. So the way I personally view identification in synthetic controls, it is like given pre-treatment outcomes, right? Selection to treatment is as good as random. Or if you don't like that, you don't want to take a stand on selection to treatment. It is like given pre-treatment outcomes, right? I have this kind of like weight, I can construct a weighted average that is stable over time. So it's a functional form assumption. Right? So whatever, is like, whatever happens before treatment takes place, I can learn the weights, and these weights are valid forever in the future, right? Which is kind of a functional form restriction, right? So it's hard for me to understand identification, that word, but that's more or less what's going on. So there is a new paper by Hido Imbens, Susan Athey, Dmitry Arkelowski, and all the other names, and Stefan Wager, and another name that I don't know how to pronounce, we start with H, right? They have the synthetic difference and differences, which is trying to combine DID and synthetic controls together. They do not allow for staggered treatment adoption in that paper. And all the inference procedures requires the number of pre-treatment periods going to infinity and the number of post-treatment periods going to infinity. So I have to have a long panel, like long in the past and in the future, and many units. So that paper is trying to do that. My biggest complaint about that paper, it is that, that paper, in my view, it is not synthetic control, and it's not difference and differences, right? Because it doesn't involve parallel trends, but it's kind of like a combination of some features of both. That's gonna play around with that. But what I like, there is a new paper by Jess Rothenstein, Avi Feller, and Eli Ben Michael. They have two papers, one at JASA and one in Royals, JRSSB, that they are doing synthetic controls in the style that Callaway and Sant'Anna, right? So they have, I mean, they allow for staggered, in the Royals paper, they allow for staggered adoption. And doing synthetic controls with staggered adoption is very tricky. They figure that out, right? They do some trick, and they select a comparison group in a transparent way. So that is my favorite paper among all synthetic controls paper. So it's like, I think it's Bain-Michael, Feller, and Offenstein. Right. So yeah, I'm gonna write in the chat, if you just Google Avi Feller webpage, right? And that's will give, I mean, and they have software, they're very open as well to discuss. So that is the closest thing I have seen in synthetic controls to this word. So I have a very long answer, and I'm pretty sure I haven't answered your question, but I mean, that's the best I can do at the moment.
Andres, you have a question?
Yes, hello, Pedro. My question is, what happens if the treatment timing is not random, if that affects the results? And for example, let's say that I have some covariates, and let's say that the treatment timing depends on population. Would that like solve the problems or not? Thank you.
Yeah. So when treatment timing is random, right? Difference and differences leaves way too much money on the table. So that's the first thing. So if treatment timing is random, is as good as random, right? You can do much better than difference and differences. And this is what I did with Jonathan Roth and this efficient staggered paper, right? So if treatment is actually random, we can do much better than DID, like 7 times shorter confidence intervals. That's much better, right? So because difference and differences is not milking all the assumptions about random treatment time. And why this is a good, what is like, how this connects to your question? This connects because like DID, so or Callaway and Sant'Anna, Sun and Abraham, we do not require treatment timing to be random. As long as we have parallel trends, we are good to go. Random treatment timing, it is a sufficient condition for that to happen, right? But if you know that happens, we can do better. So that's first thing. We don't have to have random treatment timing. Now, if I have like observed characteristics are perfect predictors for treatment timing, you are in the worst case because then you don't have overlap. Right? So suppose like every man, it is treated in period 1, and every woman, it is treated in period 2, right? And I don't have random, this is deterministic. So I don't have this overlap assumption. So I mean, at time period, I cannot switch, I cannot construct counterfactors for men under other assumptions. Right? So this is a lack of overlap condition. The only way you can bypass it is by making functional form restrictions. Difference and difference is going to work. I mean, it's going to run, but essentially it's going to extrapolate, right? But you have to be much more careful on interpretation. So when observed characteristics are perfect predictors for treatment timing, the overlap assumption is violated. So everything we do has to be very careful. So IPW, not going to work. Right? Because you're going to divide by 0. Regression is going to work because regression is very easy to extrapolate. So yeah, that's my take. Does it help?
Yes. Thank you. Maybe it's bad news about hearing about the last.
So the way I usually do it is like this, right? So in some situations, right, so if some covariate is a very good predictor, but I still believe in parallel trends, unconditional on that covariate, so let's put it this way. If man is always treated in period 1 and woman is always treated in period 10, I cannot control for gender, right? Because if I control for gender, I'm going to have violation of like overlap. But what I can do, I can say, well, treatment here is like, I'm going to have some quote unquote redefined treatment. Treatment is going to be something like being a man in period 1, right? So it's going to be, you're going to have to play around with that to redefine a little bit further to move forward. That's the way I have seen people doing it. And I think that's fine. But you should not include gender as a separate regressor, because that's what's going to be problematic.
Okay, thank you.
Pedro, just one final question. So how do you see, you have a recent paper in which you try to tackle the continuous treatment case, right?
Yes.
So what would be your suggestions? I mean, I didn't have the chance to read the paper, but do you find that when you have focus on the continuous treatment case, there are a lot of difference with what you have already done for the multiple treatment case, or the generalization of your work with Callaway?
Yeah, so the continuous treatment, it is the toughest one, because so with Brent, we could solve several problems of 2A fixed effects, right? Because it's about more or less making the wrong comparisons. With continuous treatment, it's all going to come to what parameter do I care about? Do I care about treatment effects in levels? It's like exposed to dosage A versus no dosage. So it's a kind of like the total effect of the dosage versus no dosage. If that is the case, we can solve many of the problems. But if you care about the incremental effect of a dosage, so like dose A minus dose A minus 1, those incremental effects, we can solve that, right? So if you care about this marginal causal response, or kind of like average derivatives, the assumptions you're going to have to make are much stronger, right? So the paper, well, at the moment, the continuous treatment paper is telling, well, first you have to tell me what you care about. It is a kind of like a incremental effect, like a slope effect, or a level effect, right? So if you care about the level effect, we can do a lot of solutions. We don't discuss the solutions in the paper at the moment because we rush to put a first draft out. But I mean, in the next 2 or 3 months, we hopefully want to have like an updated version with many solutions as well. So levels, we can solve it. But levels, 2A fixed effect, going to have negative weights, right? So that's the thing. Now slopes, 2A fixed effect is the same specification, but you're going to recover weighted average of slopes. These slopes weights are all convex. You don't have problem of negative weighting. But you have an extra term we call selection bias, right? Because difference and differences is a kind of an ATT type of is recovering an ATT type of parameter. So it's very local, right? So in the continuous case, I'm recovering the effect of observing like dosage A among units who actually receive dosage A, right? But what I want to do is like, I want to see like the incremental effect of dosage A among those who actually, so I'm comparing apples and bananas sometimes, right? So it's like A among those who have A, and if I subtract that like minus B among those who receive B, I'm changing both the dosage and the conditioning set. So I'm moving 2 things at the same time. I want to move only one. And once I move only one, the selection bias kick in. So in the paper, we discuss how you can strengthen the assumptions of to rule that out. So it's a sad result because I don't have any clear way of fixing it because it's a fundamental problem of like the method not being able to recover it. So yeah, so the way I see the continuous treatment is a whole new world because this problem appears even with 2 periods. You don't have to have variation treatment timing. You're back to like 2 periods, but you have multiple groups, dosage groups, then you have these issues. Some problems we can solve. The weighting problems we can always solve. We can always pick the weights we want. That's easy to solve. The hard one is like, well, how I can kill selection bias terms. That only by assumption, right? So now we like playing around what kind of assumptions we can actually make to kill it. We have been flirting with the idea of kind of trying to do something like RDD style. So have like zero local selection bias, right? But I'm struggling a lot with that idea, because if I care about one point only, that works. But if I care about several points, the whole curve, I mean, that doesn't work, because if A is close to B and B is close to C, A has to be close to C. So the transitivity of equality messes everything up. So that's where we're struggling at the moment on how to solve it.
Well, Pedro, thank you so much for all the time that you were giving us.
Sorry, Stanislao, can I do a very quick question? Sorry,
Yes,
Pedro.
sure.
Sorry, Pedro. One question: what would you do when you want to look at heterogeneous effects within the Callaway and Sant'Anna framework? I saw the paper that you have in the agricultural resources. Sorry, I don't
Yes.
remember exactly the name of the journal. But basically, what you were doing there is to do a subsample analysis, but then you cannot actually test for the difference in the coefficients from both samples. So what would you suggest to do in that kind of setting?
So you want to do heterogeneity. I mean, so that's the thing. So heterogeneity with respect to covariates, right? So observe covariates.
Exactly. Basic covariates measured before the treatment.
If it is discrete, you can do. If it is discrete, you can do subsample.
Yeah.
Right. So you can subset the data in the different subgroups, run DID in each subgroup, and you can take the difference and test if the difference is equals to 0.
But you cannot get the covariance between both estimates, no? From both subsamples. So
the
covariance
is 0.
Of that difference?
The covariance is 0 because if they are observed characteristics, they are non-nested.
Great point.
Right. So the non-nestedness helps here.
Great.
So once if the subsets are non-nested, you're good to go. You only care about the main diagonal.
Exactly.
And that's how it solves, right?
That's beautiful. Beautiful.
Yeah.
Then I can create the p-value. Perfect. No. Now it makes
Yes,
sense.
that is
Before
works.
I just had the coefficients and I couldn't say whether they were significant or not.
If the covariates are continuous, we are working on a projection approach, right? So I mean, this is going to work if covariates are low dimensional as well, like 1 or 2 covariates. You can do 1 conditional DID per time. We are currently working on how to do Kate, the conditional ATT, where the conditioning is like kind of like projecting the influence functions onto the covariate space.
Perfect.
It's kind of like you get before you average Callaway and Sant'Anna in the last step, we create an artificial outcome with the influence function, the recenter influence function, regress that on your covariate X1. That's gonna give you like OLS, and that's gonna work. So that's kind of like what Abadi did in 2005 in the last section of the paper, right? They have this idea of like, running like OLS after difference and differences. Perfect. So we're trying to do that in a double robust way. So hopefully, I have our results ready to go. I have our proofs ready to go. I have presentations ready. I just don't have a paper. Yeah, because writing the paper takes forever.
Yeah, I know about that. Makes sense. Yeah. And a very basic question. So I always have some problems with understanding what is actually the event study coefficient that you get from -1 or minus t minus d minus 1, if you have anticipation. So that coefficient is just the difference between treated and control without thinking of any difference with other relative year, or how do you interpret that -1? Because from the ATT definition that you have, basically everything is relative to -1, and you're taking difference of ATTs relative to -1.
Yeah, so the thing is that for the identification formulas change for positive event time and negative event time, right? Because for future, I need to fix the pre-treatment period because I don't have comparisons. But for the past, I don't have to do that because for period t-1, what we are doing is taking the short difference. It's like t-1 minus t-2.
Perfect.
So everything that we have in Callaway and Sant'Anna for pre-treatment periods, the negative event times are short differences.
Got it. Got it. Now it's perfect.
We're not,
Now it's
yeah,
clear.
I mean, so many people fix the estimate, they fix the formula, right?
Uh-huh.
And they go in time. We fix the identification argument, but that gives different formulas,
Mhm.
right?
Makes
So this is the kind of like asymmetry we face.
Oh, perfect. Super clear. Thanks, Pedro.
No problem.
Thank you, Pedro, again. Thank you, everyone who was following the discussion. I think this is a very amazing topic, and we will be able to go over these issues in November when we are
Yes.
we are having the course.
And hopefully by then I'm gonna have more papers out of this. So all this discussion is gonna be solved.
No, it's crazy. You finish reading one paper, and next week there is another one, staggered definition. It's forever.
I told Jeff, I wrote to Jeff, like, Jeff, please focus on the other papers. I mean, you're too big. Leave some space for me. I mean,
Yeah, makes sense. Oh, thank you, Pedro.
thank you guys.
Okay, thank you, Pedro. I will send you an email to remind you about the presentation.
This is like, yes,
And
sounds good.
Let's keep in contact for solving the matter for the course. And thank you, everyone.
Yeah, absolutely.
Again,
Thank you.
We're very happy with super useful presentation. Let's meet the next meeting of the seminar on Wednesday. And thank you, everyone, for keeping until now. Thank you, Pedro, again.
Thank you.